Hi, my name is Bradley DePippo. This is problem 19.3 from free energy and thermodynamics. So the problem is calculate delta G at 298 Kelvin for a mixture of 1 atmosphere of nitrogen gas, 3 atmospheres of hydrogen gas, and zero point 0.5 atmospheres of ammonia gas, and being used in the Haber process to make ammonia. The given variables are the temperature, which is 298 Kelvin, the partial pressure of nitrogen, which is 1 atmosphere, the partial pressure of hydrogen, which is 3 atmospheres, and the partial pressure of ammonia, which is zero point 0.5 atmospheres. The problem is asking for us to solve for the change in free energy. So there are generally two forms of the free energy equation that we need to use. One being delta G equals delta H minus T delta S, or delta G equals delta G at standard conditions plus RT times the ln the natural log of Q. Now, in this particular case, the second equation makes more sense because all of the given variables can be used to solve for the different variables in the equation. So Q can be solved for using the partial pressures given to us of nitrogen, hydrogen, and ammonia. The temperature is given, R is a constant, and delta G at standard conditions can be determined using a balanced version of the chemical equation and the textbook table for standard thermodynamic quantities for selected substances at 25 degrees Celsius. So, solving for Q, first we need to balance the equation. So the unbalanced form is nitrogen, hydrogen, equilibrium with ammonia. So start with nitrogens. There's 2 nitrogens on the left. There's 1 nitrogen on the right. So multiply ammonia on the right by 2. And then we see there's, after you multiply the ammonia on the right by 2, you have 6 hydrogens on the right, but only 2 hydrogens on the left. So you need to multiply the 2 by 3 to balance out the hydrogens. So then the balanced equation comes out to N2 plus 3H2 equilibrium with 2NH3. Now to solve for Q, you just put the partial pressure of the products over the partial pressure of the reactants. So in this case, NH3, and since the coefficient is 2, you square it over N2 times H2 cubed, because the coefficient on H2 is 3. And you plug in the values, the Q value comes out to 0.0093. Then we have to solve for delta G at standard conditions. So first we need to consult the chart in the textbook for delta G values for ammonia, nitrogen, and hydrogen. The delta G value for NH3 is negative 16.4 kilojoules per mole. The delta G value for N2 and H2 is 0 kilojoules per mole. Now we need to plug those values into the equation shown on the screen. Delta G standard reaction equals the sum of the moles of the products times the delta G of the products minus the sum of the moles of the reactants times the delta G of the reactants. So plugging those in to the equation below, you can see on the screen here, it comes out to negative 32.8 kilojoules. So now we have all of the appropriate variables to plug into our equation. So we have delta G at standard conditions, which is minus 32.8 kilojoules, R, which in the kilojoule form is 0.008314 kilojoules per Kelvin mole, temperature, which is 298 Kelvin, and Q, which is 0.0093. Now, plugging it into the equation below and doing all the math, the appropriate multiplication and the addition, comes out to minus 44.4 kilojoules per mole. And the significant figures, we're going to take the 1 decimal place from minus 32.8 because it's addition. So it should be 3 significant figures with 1 decimal place. So it's minus 44.4 kilojoules per mole. And that is the answer to the problem.